So how to name bicyclic compounds? Bicyclic compounds, these are compounds that are made up of two cycles. The two cycles can have different, they can be attached to each other in different ways. The two cycles can be fused together. So as you can see here, I have two cycles. This is going to be cycle 1 and that is going to be cycle 2. And these are fused together by two carbons. We're going to call this a bicyclic. This is a 2. Bi stands for 2. So I have a bicyclic compound, but this is a fused bicyclic compound. And then I have another type of a bicyclic compound. That other type of bicyclic compound here where I have two cycles. See, this is going to be my first cycle in here. And this is going to be my second cycle in there. And these two cycles are connected to each other by two carbons in there and a bridge. So we have two carbons and we have a bridge in here. Do you see that? The bridge. This is called a bridged bicyclic system. This means that the two cycles are connected to each other and there is a bridge coming off in there. These carbons are shared between the two rings in there. And then I have another type of a cyclic system, and that cyclic system, this is also a bicyclic system, but it goes with a different method of naming because the two cycles, they are connected to each other by only one carbon. With these, the cycles are connected to each other by two carbons. One of them is fused, the other one has a bridge, has carbon coming off of the cycle, of the two carbons in the cycle, or the two common carbons. And the spiro cyclic system is a system where you have the two cycles connected only by one carbon. So let's start by naming those bicyclic systems. To name the fused bicyclic alkanes, the first thing that you would need to do is count all the carbons in the cycle, both cycles, all of them, including the connection points. So including the connection points, that will be 10 carbons. Go ahead and put the name. The name is going to be decane in that case. Then, since this is a two cycles that are connected by two carbons, then I'm going to call it bicyclo, and you're going to put the name bicyclo at the beginning. Bicyclo is important because it tells me how many cycles are there in this cyclic system. So it tells me that I have two cycles in this case. And then you're going to open your brackets. We're going to skip the two carbons in common. So we're going to count the carbons that are on the sides of the two carbons in common. So see those two carbons in common? We're going to ignore them. We're going to ignore them. And we're going to check how many carbons are there to their sides. So on this side, I do have 4 carbons. Okay, and on the other side I have 4 carbons. So go ahead and arrange the number of carbons on both sides from the more to the less. I have 4 carbons on this side, write it down. I have 4 carbons on the other side, write it down. Between the two carbons I have nothing, 0. That 0 indicates that I have a fused system. If I had a number in there, it will be basically a bridged system. So that 0 is important. Don't skip it. Don't neglect it. You have to put it in there. Close the brackets and that will be your name. Bicyclo 440 decane is the IUPAC name of Declin. Declin is a common name for this structure. Let's have another example. Count all the carbons, including the carbons in the common, or the common carbons between the cycles, and that is going to end up to be 9 carbons. So 9 means no name, put it at the end. It's a bicyclic system, put the bicyclo at the beginning, open the brackets. Neglect the ones in the in common. So the ones in common in here, we're going to neglect those for now. And then we're going to count the ones on the side. So I have 3 carbon on this side. I have 4 carbon on this side. Go from the more to the less. So 4 carbons. and then 3 carbons, and then in between the 2 carbons in common I have nothing. This is a fused cyclic system, and then this is going to be the name. Now if you have a bridged bicycloalkanes, we're going to do the same thing, but the only difference is that once you reach the point where you want to count the number of carbons in the bridge, you have to do this. So here in this example, count all the carbons, the numbers of all the carbons, including that one in the bridge, and that will be 8, so it's going to be octane. Now on this side, I have 3 carbons, so that on this side I have 1, 2, 3 carbons in there. Use another color. So this is going to be 3 carbons on this side. I have 2 carbons on the other side, and then I have 1 carbon in here. So 3, 2, 1. Always you arrange the numbers from the more to the less. 3 to 1 in there. And then you go ahead and you write the name. These are more examples in here for the bicyclic system. These are examples of a bridged bicyclic system. So locate your 2 carbons in common, and then count all the carbons in the cycle. So this is 1, 2, 3, this is 4, and this is 5. So it's going to be pentane. Put bicyclo, open the brackets. I have 1 carbon on this side, 1 carbon on this side, 1 carbon on that side. So you arrange them like this. On here, it's a 6 carbon bicyclic system. This is my 6 carbon. And then on this side, I have 2 carbons. You put the 2 here. On this side, I have 1 carbon. You put 1 carbon in here. And on this side, I have 1 carbon. You put 1 carbon in there. It really doesn't matter which one is the ones. This is just a bridge where you have 1 carbon coming off. Here you have 2 carbons coming off. So I am having 2 on this side, 2 on this side, and then 2 carbons on that side, and then count the carbons for the whole structure in there. Let's say if you are given the name. So let's say here if I'm given bicyclo 2,2,1-heptane, and I want to go ahead and draw the structure. The first thing that I want you to start drawing is the point of connection. I know that I have a bridge of 1 carbon in here, right? This is the bridge of the 1 carbon. The first thing I want you to draw is the point of connection, and always the point of connection for the bicyclic system is 2 carbons. Okay, this is always the case. Now on one side I have 2 carbons, so you just draw 2 carbons. On the other side I have 2 carbons. This is going to be my 2 carbons. And then the bridge is going to be 1 carbon. You just draw 1 carbon up there, and then you go ahead and you connect them together. So I'm having all of these connected together like that. So this is my connection, and then the bridge is going to be coming off the 2 points in common. One thing I want to say, to represent normally a cycle of 6-membered ring, we represent it, and it's a chair conformation. The chair conformation is the most stable conformation, and here in this case I'm not drawing the chair, but I am drawing also a puckered conformation, which is stable. So to represent a cycle of 6-membered rings, when you are doing the naming of bicyclic system, please represent the cycle of 6-membered rings in this form over here, which is equivalent to the chair conformation. So this is a 6-membered ring. This is equivalent to a cyclohexane. It's the same thing as the cyclohexane in there. And that type of chair conformation here, this is equivalent to the actual chair conformation that we've talked about, but normally this is easier for the nomenclature. So please represent a cycle of 6-membered rings as this conformation in here, to be a puckered, more stable conformation. And this is why you're seeing me drawing all the chair conformations or all the cycles that have 6-membered rings as a puckered conformation like this, just to relieve the energy of the structure. Same thing here. If I want to draw this, the first thing I would do, I would draw the 2 points in common, and then go here. On this side, I have 3 carbons, so I have 1, I have 2, and I have 3. And on this side, I have 1 carbon, and on the other side, I have 1 carbon in there. And then connect everything together. Don't connect the 2 points in here, because this is going to be whatever bridge is coming off these 2 carbons. These are the 2 points in common. And then go ahead and do the connection in there. So here you go. This is going to be my structure, and this is how it's going to look like. Okay. For the bicyclo undecane, you go ahead and you draw the 2 points in common. This is the 2 points in common. Let me put more space in here. So you have your 2 points in common. And then I do have 4 carbons on this side. So this is going to be carbon 2, 3, and 4. And 4 carbons on the other side, 1, 2, 3, and 4. And then go ahead and connect them. And of course I have a bridge all the way to the top. So this is going to be it over here. And then I have a bridge of carbons on the top. So this is going to be my bridge over there of 1 carbon. If you have a substituent, then you number the bridge ring system beginning on the bridge head. This is always the case. So here you go. This is an example. These carbons are the bridge heads. These 2 are the bridge heads. So when you have a bicyclic system, you start numbering from either one of those. And always we want to give the substituents the lowest number, but we have a method of doing so. So you cannot start numbering from the low carbon cycle side. You have to start numbering from the most carbon cycle side. So this is why I started my carbon 1 here. I have a carbon side here that has 4 carbons. The side here has 3 carbons. So I have to move along the side and give it the lowest number, even if my substituent is on this side. I just ignore it. So start always from your bridge head and move along the side cycle, or the side cycle that has more carbons in there. If there's a possibility to give, in that case, if there are substituents and you can give them the lowest number, go ahead and give them the lowest number. So let's say if I have a substituent in here, then in this case I need to start carbon 1 here and go 1, 2 to give that substituent the lowest number. So that is going to be 1, 2, 3, 4, 5, 6. See, I started with 1 bridge head connection and I ended up with the other. I cannot skip it. And then that is going to be now, whatever comes next is going from the most carbon side to the least carbon side. So here I don't have a bridge, but if I had a bridge of 4 carbons, I have to continue through that bridge. Because 4 carbons is more than 3. But here I don't have any bridge. I have 3 carbons, so I have to continue along that side. It's going to be 7, this is 8, and this is 9. So naming it, just go ahead and name it as regular bicyclic system. That is going to be bicyclo, it's going to be 4, it's going to be 3, it's going to be 0, it's going to be nonane, and then put the substituents at the beginning, 8-methyl. Same thing over here. This is my bicyclic system, but now the difference is that I have a bridge coming off carbon 1 and 5. So you start from the points of connection, you start carbon number 1. So you go along the side that has more carbons. So the side that has more carbons is here. Here I have 4. Here I have 2. Here I have 1. See? So you go by 4 here, you number that, and then you keep numbering along the side that has 2 carbons. And then the side that has the least number of carbons, you leave it till the end, even though it has a substituent on it, and then put the name. With respect to the spiro, for the spiro, just to differentiate the naming of the spiro and the bicyclo, we're going to go the opposite. So when you start numbering, you don't number the joint carbon. Never do this. Just go ahead and number the carbon side that has the least amount of, or the least number of carbons. So in this case, when I am naming it, It's going to be spiral because they are connected by one carbon. Count the total number of carbons including that common carbon. That's going to be 7, so it's going to be heptane. Open your brackets and arrange the carbons from the sides of this common point from the low to the high. This is the difference. So from the low, I have 2 carbons on this side. I have 4 carbons on the other side. This is going to be spiral 2,4-heptane. If you have a substituent, then you're going to give your substituent the lowest number, but not before numbering your lowest carbonate chain first. So notice here what I did. What I did over here, I had to, so you start, okay, let me erase those. Okay, they don't erase with me. Okay, yeah, probably I moved it. So this is gonna be, so you start here with 1. This is carbon number 1. Why I started with 1 here? I started with 1 over here because this is gonna be the side where I have less carbons on this side chain, or on this side cycle. I have less carbon, so I have to start 1 here. I cannot go 1, 2 because my first cycle is here. So I cannot skip it. You cannot skip your cycle. So your first cycle is here, finish it. So it's going to be 1, 2, and 3. I am done from my first cycle in there. Now I have the option to go 3, 4 or 3, 4. Just to choose the option to give your substituent the lowest number. So that is going to be 4-methyl in that case, and then name it as spiral because it's 1 point in connection. I have 2 carbons on this side, I have 3 carbons on the other side, and then your total number of carbons in the chain. With oxidation reduction, oxidation is the increase in the number of oxygens, decrease in the number of hydrogens. And reduction is the increase in the number of hydrogens and decrease in the number of oxygens. So a CH4, a methane, exists in its most reduced form. And the most oxidized form of methane is carbon dioxide. As you can see, as I am oxidizing, O stands for oxidation. As I am oxidizing, I am increasing the number of oxygens. So a carbon double bond O in reality is a carbon that is connected to 2 oxygens. So here I'm increasing the number of oxygens, until I reach here having 4 oxygens, 2 here and 2 there. So this is the most oxidized form of carbon. If I go in the opposite direction, I do reduction. Reduction is abbreviated by an H. This is what reduction is. And reduction is basically the decrease in the number of oxygens or increase in the number of hydrogens. So I am decreasing the number of oxygens, increasing the number of hydrogens as I go. Alkanes, we're going to study alkane reactions possibly either at the end of this semester or in organic too. We're going to see if we have more time. But with respect to the only alkane reaction that we're going to talk about here, that is going to be combustion of alkanes. This is the burning of alkane in presence of oxygen. This is the general formula for the reaction. N is the number of carbons. So if I give you a structure, you have to convert it into a molecular formula to figure out what is this N, to plug it in so that you can apply this general formula and write down the balancing of the equation. Sometimes the balancing of the equation is really takes time, so it's better for you to know the general balanced equation. When alkanes burn in presence of oxygen, they produce carbon dioxide and they produce water, and of course they release energy. This is an exothermic reaction.